Hello students, welcome to this video on volumes and finding volumes using calculus. We're going to introduce volumes with volumes of known cross-sections and volumes of revolution. These are two different methods we can use to find volumes using calculus. So the first method is called volumes using slicing or known cross-sections, and that is what this video is going to be about. And we have another method called volumes of revolution, that will be for another video. So volumes of known cross-sections or volumes of slicing, volumes using slicing, relies on this principle, and actually both of these methods rely on the same principle. We find the area of a representative slice, and that representative slice, you can think of it for this pyramid here, it would be a square. We'd have this square slice of this pyramid, and we find the area of this slice, and then it has a really tiny volume because it has a little tiny width right here. So we have a volume, a thin sliver of volume, you can think of it as, and then we sum up all of those volumes from the bottom to the top, and we get the entire volume of the whole thing. So with known cross-sections, all we have to do is figure out what is the area of this representative cross-section, and then or what's a formula for the area of it if that area is changing, and then we can sum those from the top to the bottom, or the bottom to the top, or from the left to the right. With volumes of revolution, you have every time some kind of region that's being revolved around an axis, and then once you figure out what your slice is going to look like, and the nice thing about volumes of revolution is every time your slice will either be a disk or a washer. So it'll be something circular because you're finding that volume by performing a revolution of a function about an axis. The difference here with known cross-sections is we could actually have like a square cross-section or really any shape cross-section we want. So using calculus to find volumes, like I said, think of it as slicing a big region up into a bunch of pieces, and then the volume of the slice, so the volume of this ith slice right here, whatever we call it, the first slice or the second slice or the third slice, so we're calling this the ith slice, is approximated by the area of this piece right here, so the area of this rectangle, times delta x. This is delta x, that's the width. So the area, a of x, of that thing, times delta x would give you the volume of that piece. Okay, and then if we repeat this process for each of those slices, we would get an approximation for the total volume. Right? The volume is going to be the sum of all of those areas, or all of those volumes actually. The volume is the sum of all of those volumes, but they're very, very small slivers of volume. Adding all those slices together gives us a better approximation, and the exact volume can be found with an infinite number of slices. So this is the same thing we did when we defined our Riemann sums. Okay, the infinite limit of a Riemann sum is known as the definite integral, so we can find the exact volume of a region by finding that approximating cylinder, figuring out what is the area of the cylinder, and times the delta x gives us a volume of a small thin cylinder, thin slice, and we sum all of those from A to B. So here's an example using known cross-sections. Our first example. Imagine we have a 3D object with a parabolic base. We want to find the volume of this object if, first of all, cross-sections are semicircles, and second, cross-sections are squares. Okay, so first of all, we have cross-sections that are semicircles perpendicular to the y-axis. So let's draw what that's going to look like. This is our region, our parabolic region right here. And if we have cross-sections that are semicircles, well, that's going to give us this. Okay, they're perpendicular to the y-axis. So you can think of a semicircle, think of this as like a loaf of bread, and if it were laying on this side right here, okay, then it would sort of be sitting on the table, and it would have a rounded top to it. And it would be bigger on one side and smaller on the other side. So it kind of looks like a loaf of bread you might get at Central Market or something like that, like a half of a round loaf. That's the best thing I can think of to describe it as. So imagine that you have these cross-sections that are semicircles, and they're perpendicular to the y-axis. So they're cutting the y-axis like this. Okay? And put one more in here. Alright. So we know that those are our cross sections. We know that our parabola is described by the line y equals x squared. So what we need to do is we need to come up with a formula for the cross section. So come up with a formula for this area of my representative slice. That's what you want to do on each of these problems. Come up with a formula for the area of your representative slice. Okay? So I want area, and I know that, well, area of this half circle is going to be 1/2 of pi r squared. And my radius from here to here is just the value of x at that point. So this is equal to 1/2 pi times x squared. So that wasn't too bad. But now if you think about it, you're summing these from here to here. And that's up from 0 to 4, right? Up to 4. So 0 to 4, and that's in the y direction. So we know we want a dy integral. So I need that x in terms of y. So what I want to do is rewrite that in terms of y, and I can do that because I know that x squared is the same thing as y, right? So I have area as a function of y now becomes 1/2 pi y. 1/2 pi y. And now I can sum those. So if I do that times delta x, that would give me my volume of this little piece, this little slice. And if I integrate 1/2 of pi y dy, remember the dy gives me that infinitely small width of my cylinder, of my little slice. And I'm integrating those from 0 to 4. So I'm summing from 0 to 4 all of these little tiny slices, and their volume is 1/2 pi y dy, essentially. Okay? So this just becomes, we can pull the 1/2 pi to the outside. We have integral from 0 to 4 of y squared dy, which would be 1/2 pi when I'm sorry, that's just y, not y squared. And that's going to end up being y squared over 2. That's where I was going with that, from 0 to 4. And that would be 1/2 pi 16, or if I plug in 4 squared is 16 over 2 is 8. So this just comes out to 4 pi for that volume. So that is the volume of this object if cross-sections are semicircles perpendicular to the y-axis. Next we want to look at cross-sections that are squares. So let me redraw this region for you. It's a little skinnier this time, but oh well. And now our cross-sections are going to be squares, again perpendicular to the y-axis. So they're going to look like this, more or less. Okay, and let me put another one in here. Okay, so if you think about it, this is kind of what your region looks like now. Alright, so it looks something like that. So it has squares, square cross sections. Put one more in here. Okay, so that's what the region looks like. So now what I want to do is, again, I want to find the area of this thing, and I want to sum all of those from 0 to 4. So my integral is still going to be in terms of y. So I need all of this, whatever my area expression is, it needs to be in terms of y again. Okay? So if you think about it, the area of a square is side squared, right? Side squared would be the area of a square. And if we can express that in terms of x first, and then we'll translate that to y, this length from here to here would be x. So the length from here to here, one side, is 2 times x, right? This is x, and this is another x. So this is equal to 2x squared. That's the area in terms of x. So if I was writing area as a function of x, I would have the quantity of 2x squared. But I want that in terms of y, and remember y is equal to x squared. So I could rewrite that as x is equal to the square root of y, right? So instead of x, I can put in the square root of y here. So if I want this as a function of y, which I do because I have a dy integral, then I need 2 times the square root of x is, x is the square root of y, right? and that all squared. So that would simplify 2 squared is 4, and the square root of y squared is just y. So that comes out to 4y. So the area in terms of y is 4y, or the area in terms of x is the quantity of 2x squared. We could have also just written this as 4x squared, right? And then you know x squared is the same thing as y, so that would become 4y. So that may have been an easier way to think of it. Okay, but the area comes out to 4y when it's in terms of y. So that's our integral. And now that's pretty easy to integrate. We have 4y squared over 2 from 0 to 4. So plugging that in, I'm going to have 4 times 16 over 2, right? Or 4 times 8, which is 32. So the volume of this thing when the cross-sections are squares is 32. And that's just like cubic units. We don't have any measurement on it, so you don't have to worry about that.